So what I'm going to do today is I'm going to continue with the curve folds, but I'm going to take a little bit of a side route to sort of start identifying important features of any surface in 2 dimensions. And then right at the end of the lecture, I'm going to come back to looking at the quantities we explored last time and actually giving meaning to them. So remember last time we set up our problem where we had, we started with a curve and we wrote down everything that had to do with a curve. And then we said, okay, on both sides, we're going to have developable surfaces. We wrote down everything that had to do with a developable surface. And then we went about and gave the most general expression for a unit vector in any direction, except that we expressed it in terms of a triad that was fixed to the curve. And then we simply worked out the consequences of the fact that it was a developable surface, as well as the fact that the curve's properties, we knew how the triad that moves along the curve changes. And then we got an expression for the derivative of r. And in that expression, we then identified other important vectors simply by looking at the expression and grouping things together and looking in front of the phi prime and the theta prime and the phi prime derivatives. We identified these 2 vectors, and then we went and used those to write the whole derivative of r in terms of them. Okay. And so what I want to do today is I want to introduce the ideas of a metric and curvature, and then show you that these things actually have a distinctive meaning. Okay, and in this particular case, it is just fortunate that the things that we identified by just starting from scratch, doing the simplest possible thing, working through the problem, are in fact very important vectors in the space-time itself. Okay, and as Corlay, I think, guessed, this p hat turns out to be the surface normal. Okay, and that I'll also prove to you as we go on. Okay, so let's now have a look, if we can advance, at a metric on a parametrized surface. So what I'm going to do is I'm going to give you an idea of I'm basically going to give you the formula for the metric in the special case. And then when we do the more general derivation that I use WALD for, you'll see the most general expression for the metric. But this is a metric that you can get in the 3-dimensional case. And once you've got it, there are already a tremendous amount of things you can actually do with it. Okay, so historically, people used to that worked with surfaces in 3D, used to speak of the first fundamental form. In fact, this is for any surface. The first fundamental form and the second fundamental form. And the first fundamental form has to do with how you measure, and the second fundamental form has to do with how the surface is actually curved. And so I'm actually going to give you, just simply in terms of the parametric surface, the definitions for both. And later you'll see it's a special case of a much bigger set of properties. So if you're given a surface, it's parametrized with specific coordinates in the case. So what usually happens is we label our coordinates with indexes. In this case, we have x1 is just s and x2 is just u. Okay, and the surface we have, remember the surface is a parametric expression, so this s actually stands for a vector of s and u, and so it's actually the 3 components, okay? And once again, we can label the components themselves. It's in 3-dimensional space, so that index runs from 0 to 3, and the index that goes for the coordinates runs from 0 to, if you don't use time, usually it runs from 1 to 3. If normal space, often we use the index 0 for time or index 4 for time. So I'm talking about the future right now. Anyway, so this index goes from 1 to 3 for the 3 dimensions of space. The index for the coordinates on the surface goes from 1 to 2. Okay? And so we have our indexes 1 to 2, and this index goes from 1 to 3. And then what we do is we define the metric or we basically can compute the metric. It's definitely not the most general definition for the metric. is simply the derivative of s with respect to xi dotted in with the derivative of s with respect to xj. Okay, so you can see because I goes from 1 to 2, there are basically, this is a 2 by 2 matrix effectively, and it's symmetric because those, it doesn't matter if you interchange those. Okay, so you take the derivative of s with respect to x, you get a vector because you have to take every single component with derivative with respect to x, xi, you take this derivative and you also get a vector and you dot it together, and that's the component of your metric. And so let's just, in the case of, what have I done? Oh, in this case we have G11, which we actually label it, it's G, that's labeled with a first coordinate. In this case it's GSS. So I'm just giving you alternative versions of the notation. Depending on your textbook, they're going to use either label it as 1, 1 or as by the coordinate themselves. You can do whatever you prefer. Just make sure you know what you mean. Okay, so GSS is the derivative of S, big S with respect to little s, dotted in with the derivative of big S with respect to little s. And so you basically have ds1 ds squared plus ds2 ds squared plus ds3 ds squared. And this G12 is then the derivative of big S with respect to S, dotted in with the derivative of big S with respect to U. And so you have this second term, and then G12 is equals to G21, and then the final one is G22 is simply GUU, so it's the derivative of S with respect to U dotted in with itself. So it's a norm of that thing. The nice thing about the metric here, if you have the parametrized version of the surface, it's straightforward to compute the metric. It's just the differentiation. And many of the tensor things are like that. You get your surface or you get your metric, and then all the quantities that are important to you, you can get by differentiating. Okay, so it's not like integrating. It's a very straightforward way, or almost algorithmic way of you get a surface, you do this to it, then you immediately know how you're going to measure on it, and you're actually going to know a lot more. And that's what I like about tensors. In some senses, when I start introducing tensors, what it does effectively, it linearizes a very big problem. So it reduces very convolved surfaces and features onto a sort of a linear representation, or several linear maps that you can do things with. But the result is that it's quite easy to calculate a lot of aspects about your surface in a structured and systematic way. So this type of thing, people knew. They solved problems like we're solving now long before Tensor or Riemann came about and developed general tensor analysis and geometry and stuff. And every time what happened then is they looked at a specific problem, tried to solve it, and then got tricks to solve that problem. And then the hassle was the next problem was a new set of tricks you had to develop. And what the tensor theory eventually did is it took all that and basically canonized everything we know about geometry. So some of these problems were known before tensor analysis was developed or manifolds were developed, but the full power of it was only happened when somebody actually structured it, like I'll introduce the stuff. I think next week I'll start actually doing the full tensor analysis introduction. Anyway, so here's the metric. This is how you calculate it. What it tells you, okay, and often when I have the metric, I store it in a matrix, okay. You can see that this metric is dependent on which coordinates you chose, okay, S and U, and the other rules of that tensor analysis actually gives you is how, if you've chosen a different set of coordinates, how to easily go from this thing to the new set of coordinates, but that will also come. But anyway, for this particular S of U, you get the metric directly from your parameterized surface. This is what it is. What it tells you, okay, and we call that the metric tensor. What it tells you is that suppose you have this in this particular case, this convolved surface, right? You have the one parameter S that tells you how to go along the curve. You have another parameter U that tells you how far you've stepped in. Okay, and suppose you describe everything on the surface in terms of those two. And suppose somebody tells you, I go from coordinate s equals to 1 to coordinate s equals to 0.5, and I go from coordinate u equals to 1 to u equals to 0.99. Okay, and they said, how far have I traveled? Right, it's 2 points on the surface, but the coordinates themselves tell you nothing about how far you've moved. Okay, what the metric does, it actually allows you to compute that directly. Okay, so the metric is an infinitesimal rule, okay, and this is the intuitive introduction of how to compute. It's like a generalized Pythagoras rule. How, if you're given the difference between, an infinitesimal difference between two coordinates or points on your surface, what's the actual distance between them? And so the thing works, or the definition is simply the distance squared if you make an increment of ds and an increment of du is just computed in this way. Okay, it's literally gss times ds squared plus 2 gsu du ds plus guu du squared. Okay, so it literally gives you Pythagoras' rules generalized. So the simplest metric we have is just the identity matrix. Okay, and the identity matrix will then just assume you're working in Cartesian coordinates, and then your distance will just be ds squared plus du squared. So that's where Pythagoras gets out. But if you're working in these strange coordinates, and I'll give you a couple of examples now, you see that these other terms actually are important. Okay, so now what I'm going to use is a metric on a ruled surface. It's just a special case of this one, but let's just go through it. So our ruled surface, remember our surface was described by the curve parameterized by s plus u times a unit vector r of s. Okay, and for our purposes, we're going to assume this curve is parameterized at the distance that it's, that is wrong. This curve is parameterized so that its tangent, sorry, that should be t. That tangent is, the norm of the tangent is 1, so it's arc length parameterized, and r hat is 1. Okay, and so what we have is to work out the metric, what we have to do is we have to work out the derivatives. So we have ds is simply the derivative of c with respect to s, that's the tangent vector, which norm is 1. Or s is chosen that the norm is 1, plus u times r prime. Okay, and what the other derivative ds du, u only appears there, and so the second derivative ds du is simply r hat. Okay, so ds is a vector that points in this direction, ds du is a vector that points in the r hat direction, and so our metric elements are GSU, which is simply t dotted in with r, GSS, which is that thing dotted in with itself, and GUU, which is just 1, right? Because we've assumed that ds du dotted in with ds du is distance is 1. Okay, so given a curve and given a directrix for a ruled surface, we can immediately work out simply from these formulas what the metric is. So let's look at an example. Suppose our curve is a circle. Suppose we're working in 3 dimensions, but we restrict the circle just to be in the xy plane. Okay, and we're going to take our parameter going from 0 to pi. So we're going to start over here, and we're going to move around here, and that's going to be our u equals to 0. And so what we now want is to define the ruled surface. You need a unit vector in addition, and let us suppose, okay, and s basically increases here. So let us suppose our unit vector is r hat equals to 0, -1, 0. Okay, so it's going to point in the negative y direction. So here, as s goes along, I construct my ruled surface by at every point basically putting a vector down in the direction of r hat. Okay, and what I'm going to do now is basically go about and put a few more lines in. So the u, as you increase u, you move further and further and further across these lines. Okay, and now what I'm going to do is I'm going to put in lines of constant u. So suppose I increase u a little bit more, I'm going to get basically just move that circle, or I'm just going to move my curve effectively down there. So what I have here is a flat surface. Okay, it's not curving, it's flat, right? But the coordinates are strange. Okay, because if I've taken the increments to be 1 over 12 pi. So from there to there is 1 over 12 pi. From here to here is a 1 over 12 pi increase in u. Okay, so let's now go about and work out the metric for this particular curve, right? We're just in a flat plane. And so if we were in xy coordinates, our metric would just be dx squared plus dy squared, or 1, 1. Let's have a look if we work out the metric. So we get GSS and GUU are just 1. Okay, because why? So GSS is t plus ur prime, but r is constant. Okay, so that's 0. So we just have t dotted in with t, and ignoring my typo, we have that's 1. The norm is 1. So GSS is just 1. GUU is just 1 as well. And GSU, right, remember, is t dotted in with r hat. Okay? And r hat is just 0 minus 1, 0. And t is just the derivative of this thing. So we have basically
sine cos 0.
Yeah. T dotted.
Minus cos and not just.
So that's minus. I'm missing a minus there. Yeah. Okay. So there's another mistake. So there's a minus cos over there. But the important thing I want you to see is when s is pi over 2. In other words, when s sits over there, that's effectively 0. Okay? And so what that tells you is this grid here is pretty square. So if you increase, it's just the normal Pythagoras rule. So if you sit here, you say increase by pi over 24 in s, or decrease by pi over 24 in s, okay? And then increase or decrease by pi over 24 in u, and then you have this little box. So suppose you go from that point to over there, the distance is just ds squared plus du squared. It's your normal Pythagoras. Okay. Now let's go and look at what happens over here.
So we say GSU is minus cos s.
Yeah.
The s that we plug in there, is that the starting point or your end point s value that you put in there?
So you're talking about infinitesimal distances.
Okay, so it's a distance.
No. So this s is the coordinate s of where you're working out your metric. Okay. And remember, this ds is just a small region around that s. Okay, so this is just, and this is where it's different from, this is just a small distance.
Yeah.
So the small distance dl going from here to there, okay, you in some sense would plug in like an average s, but because the distance shrinks, you can simply say at that point, you put the s value over there. So here s would be, what's it, pi over 2. Here s would be pi over 6. Okay, that you plug in there. So this s refers to where you are on your surface. Yeah. And so over here, you can see that's just normal Pythagoras over there. Over here, suppose you want to do the same thing, increase or decrease u by pi over 24, decrease s, or increase s by pi over 24. This distance for the same increase is different than the one inside. And that's what this cos does.
It's going to be by a factor of minus square 3/2.
Yeah, so it increases the length. And so what your metric does, it's true regardless of your changes of coordinates, right? So the metric is basically compensating for the fact that here the coordinates are not at 90 degrees to each other. Okay, so I just wanted to give you a sort of very intuitive idea of the metric. You've got flat space, you've got Cartesian coordinates, that would be the normal Pythagoras. But if you happen to express your surface in the way we usually do with ruled surfaces, where you have a distance along a curve and a distance along this ruled direction, then you've got to have these other things to actually compensate how you're measuring distance. Okay. And so if you wanted to work out the distance, say, of going from this point to that point, what you would do is you would have to integrate over your path this dl squared. Okay, so this is just infinitesimal. So a small little change over here basically is just valid at a particular point. So suppose you wanted to say, take a curve of s equals to u. Okay, wait, yes. S is 0 here, u 0 there. So suppose you wanted to go from here along the line s equals to u to over there, say, and wanted to work out that distance, then you would have to integrate dl over that particular line. Okay. Questions here?
I have a question, but it's not really relevant.
Well, then ask it.
So, we have that curve that goes like this, and then we have the lines pointing down. So is it going to be like this or like this?
It's a flat sheet of paper.
Okay.
Okay, so for this particular example, C lies in the plane.
Mm-hmm.
Okay, so that's just a curve on the plane. So it's, in fact, it's this circle over here. Okay, in fact, here I actually have it. Right, so here you have the circle. Here you have R that points down. Okay, so all that I've done is the surface lies flat. Okay, all that I've done with that thing is I've chosen S and U to be a different set of coordinates.
Okay.
Right, so instead of X and Y that says I'm at a position, say X equals to 1, Y equals 2, I tell you you're at a position 5 meters along this curve and 10 meters down. Okay, and you want to go to the position 4 meters along the curves, 2 meters down, and I want you to tell me what the distance is between the two. Okay, and then you would use this thing to measure the distance rather than Pythagoras.
Yes.
Okay, so it's literally just given a strange set of coordinates on a very flat piece of paper. Right.
So will it be this example, will the graph look exactly the same even if we were only cos s sin s and not the 0 as well, like only in 2D basically?
What do you mean, would the graph look the same if you have?
Yeah, if you only have that cos s sin s and not the 0 in the z direction.
Yeah, yeah.
So it will be the same.
It will be the same. It's a special flat case. Yeah.
Okay, so it's so I think that is why she asked that question. Because
Why?
of the 0.
Oh.
And she thought it is like 3D, but it's just a type of coordinates
In 2.
But
Okay.
it's still 3D.
So-
No, it's not.
It's just this example happens to be just the plane stuck in 2 dimensions, and that's the reason I gave the example, because you first got to sort out the very basic, the fact that you can have a strange coordinates just describing a plane, which is different from the next case. Okay, so suppose we now have the same curve. Okay, cos s sin s. Here is my y-x plane that I've just changed a little bit. And there's u equals to 0, so exactly the same problem. And now instead, and then my s also goes up, instead of having r, the 1 over here, I'm going to put it over there. Okay, so now I have my vector that's the directional vector that is at 90 degrees to the normal vector of the curve, right? The normal vector of the curve, remember, always points in towards the point at which the curve is curving around. And this is 90 degrees to the normal vector. And now you can make your little arch as much as you like, because it's the right one. Okay. So there we go, exactly the same thing, except that now my normal vector has gone from pointing in the plane to pointing up like that. And there is my trellis, right? So there is my arch dome. Okay, and so here is the U's that increase as I go further and further along the ruled surface. And I can now go about and work out my metric for that one. Okay, and remember the metric for GSS is simply, because R is constant, is simply T dot T, which is 1, GUU is 1. And remember GSU for the ruled surface was R dotted with T. Okay, and the tangent space or the tangent direction for this thing lies in the XY plane. And this thing is Y, so that's 0. Okay, so on this case, where I've literally taken this piece of paper and done exactly what Cordelet wanted to do, you know, put it into an arch, on that piece of paper, I simply have a Cartesian set of coordinates. In other words, if you go from that point to that point, it's just Pythagoras straight. Okay, so there's a very big difference between measuring actual distance and a skew coordinate system. Okay. And if you work with a metric, it just automatically takes care of that. Okay, because here all the angles are in effect 90 degrees, 90 degrees, and so you're fine. Okay.
So if the main red line, the one that we had at the beginning, is
Yeah.
that one, if that was like something like this, then it will change.
It depends if it's in a plane or not.
Okay.
Okay, you could do this and you would still, right, suppose you did that.
Yeah, that's what I mean.
Okay, so you have like a sinusoid for C,
Yes.
and you have U and you have R just equals to 0, 0, 1.
Yeah.
Then it would still be, the metric would still be 1, 1. Okay, because you simply have the distance, because you can take it and you can flatten it out to a flat plane. Okay, so there you have a nice coordinate system there. Okay. If, however, your thing did this and did a little kink like that, then you're going to have the combination of the, a little bit. So when it starts getting weird, then you have a mix-up between coordinates that are stuck to your curve and actual curvature. And so what the metric does, it gives you a recipe for going to compute how you measure distance. Okay, you literally take the parameterization, you take the first derivatives, and then you work out all the metric elements from it. Okay, so suppose you had this thing now, and you wanted to say something about how it's curved. Okay, in general. What you would do is just continue, take more derivatives. Okay, so remember when you did surfaces just in 2 dimensions, right? You would, and just suppose you had the graph of y equals to f of xy, or sorry, z equals to f of xy. Then you would take derivatives, you would find your minimum where the gradient vanished, and then you would take second derivatives to tell you whether it's curved, whether it's a saddle, or whether it's a maximum or a minimum. Okay, so what comes now is the generalization of that for any parametric surface. And so the way we do that is we define the curvature of a parameterized surface in R3, and this is the thing we call the second fundamental form. Okay, and the way you compute that is simply, suppose we have our parameterized surface, and these are the coordinates x1 and x2. Okay, and you then, another way of representing it is just S, which is basically a 3-vector of xi. Okay, so it depends on S of u and alpha, and the components of S I write like this: S alpha, S of u. So this is exactly the same as I did in the previous slide, except that now the index I goes from 1 to 2 and alpha goes from 1 to 3. And I tend to change index or type of index. So if the indexes that go over just the coordinates inside the surface, I call a certain type of Roman numeral, and this alpha is the index that goes over the 3 dimensions, the surface that the space the surface is embedded in. Okay, and this is just, you don't have to do this, you just have to, because it's often clear from where you're putting the index, where it goes from, but it's just a habit I've gotten to from GR. I tend to make coordinates that are just spatial coordinates like this, and coordinates that are a higher dimension time, that I add a different, I give it something else.
So alpha will be over 4 dimensions when we add time?
Yes, yeah. Okay, and then just to remind you, this we have already done. The normal to a parameterized surface is those vectors we're using to compute that we were dotting together to get the metric. It's just the cross product. Okay, so the normal is simply you take the derivative of the surface in the u direction, you take the derivative of the surface, the derivative of the surface in the u direction, the derivative of the surface in the s direction, you take their cross product, and then you get basically the normal to the surface. And then I wanted a unit vector, so I divide by the magnitude of there. Okay, so now the curvature is just basically, I define my curvature tensor as the second derivatives of S with respect to xi and xk. So you basically take all the possible second derivatives of your parameterized surface, and then you dot it in with a normal. So then you're going to get a scalar. Okay, so S has got 3 components. You basically, the first step is you work out what your ds dx is, and then you take that thing and you take the 2 derivatives in one direction, the other direction. And then you define your curvature scalar or your curvature tensor as simply that dotted in with your n hat, which is the normal vector. Yes?
So we have dxi and we have dxk.
Yeah.
What is the k?
K sorry, that should have been a J.
Okay. Okay.
Reason not to follow. That should have been a J.
Okay.
Okay. Yeah, so you basically take one derivative in the one direction, derivative in the second direction, and you do it. Another way, that's why I made a typo. Another way of writing this that you're also going to see, it's the sum of S. Commas usually indicate that everything that follows after it is a derivative. Okay, so it's S, the kth component of S, comma, the derivative with respect to xi, the derivative with respect to xj, dotted in with the kth component of n, summing over k. Exactly. Write it out and make sure you know what's going on. Okay, well, these things explode, but they are straightforward to program because you just keep taking derivatives and you combine it in the right way and you get the answer. Okay, so this, and often what I'm going to do from now on, it's the biggest contribution a secretary has ever made to mathematics. What happened was Einstein, you had a lot of these sums in Einstein's theory when he was working out his first paper. And at that point, they had typewriters, so they couldn't actually type the symbol. So what they did is they had to space it just right, and afterwards they would come and write in these symbols. And so what happened in this particular case is the secretary forgot to leave in the spaces. And so what they had was just this combination. And it was a lot of typing, because eventually you'll start seeing the things that come out are pretty intense. And they just they didn't want to retype it. So then Einstein said, this is my convention. Whenever you have an index at the bottom and an index at the top, it means you sum over everything that index could possibly be. Okay, so that's the summation convention. So, and that I'm going to stick to. And also be careful, this is not a matrix effectively. There's a difference between an index at the top and the index at the bottom that I'll define when I start defining the manifold rigorously. Okay, there are things that are lower behaved or transform differently from things that are up. And you can only sum if you're down and then up. You can't sum across like this. Okay, so those are rules that eventually, but for now, this thing is fine. You're just summing over k. If ever you see an index repeated down and up, it means sum over it. Okay. So this matrix that you basically compute in this way, is what we call the second fundamental form. And you once again basically have something that is called Kij dxi dxj. So exactly like the metric, except that this matrix is different in front. Okay, and this thing contains everything with respect to the curvature. Okay, so remember what we had when I said remember the second derivative, you could say whether it's a minimum or a maximum, okay? The thing that this makes possible is that suppose you have a very funny surface, right? The minimum and the maximum curvature need not point down or up. It can basically point in any direction, okay? And this thing actually allows you to see that, okay? And you're going to have an example like that where you actually work it out and see what the power of it is. But, okay, so to get the components of the curvature, take the second derivative or whatever your parameterized surface is, dot it in with a normal, and then you basically have, in 2 dimensions, you're going to have 4 components, and that's going to be your curvature tensor. Okay, so effectively for your purposes now, it's a matrix of functions. Right. Okay, so just written out, it's simply KUU du squared plus 2KS du ds plus KSS ds squared. Okay, and so you can do this, and this is where it's going to come back to the surface. You can work out your Senker fundamental form for a ruled surface. So remember, here's once again the mistake. So remember we had S equals to the curve of S plus U times R of S with R hat and T hat equals to 1. Sorry, R hat and T equals to 1. Then we had the derivatives of S with respect to S was simply T plus UR prime and S comma U, which is equals to R hat. And then what we want to work out is the second derivative. Okay, so the second derivative of S with respect to S is just the derivative of this guy. So that's T prime plus UR prime prime. Okay, and the derivative of S with respect to U, okay, ds du, you can either take this one and differentiate it with respect to U, so you just get R prime, or you can take this guy and differentiate it with S, and you also get R prime, so that's R prime, and ds prime du is just 0, okay? And this thing means, remember that you said at every point you have a line, so this you can immediately see the direction in which your line is. Even if somebody gave you a ruled surface that wasn't in this form, right? You can change coordinates. Suppose you had S of S and U written in this form, and then you said, okay, I want to write it in a different way. So I'm going to say let T equals to S plus U and V equals to S minus U. So I'm disguising my ruled surface. How do you find out if it's a ruled surface?
So if you need a ruled surface, you need to prove that.
Yeah.
So you multiply it out and see what you get.
Yeah, you basically take whatever thing you've got, work out the second derivatives, so you work out the curvature, and then you might still not get zeros here. But then when you take the eigenvalues of the curvature, you'll always kick out that you have a 0 in one direction, and then you know it's a ruled surface. Okay. Right, so this is simply the definition of the curvature.
So you can use that to also test for ruled surfaces?
Yes, it's a better test for ruled surfaces. You can either, immediately if it's in this form, you can say, fine, it's a ruled surface. But you can also work out the curvature. And the moment you can prove that the one eigen direction of the curvature has an eigenvalue 0, then you have a ruled surface. Okay, so now we have the derivatives of these S's. But to work out the curvature, you have to project it onto the normal vector. So we basically work out our normal vector, which in this case is just R cross T. Okay, so here basically comes the proof of what P actually is. Okay, so remember the normal to the surface is simply the SDU cross the SDS over normalized to 1. So the SDU is R hat cross the SDS, but because R is a unit vector, R prime is orthogonal to R. Okay, that you've proved already. Okay, so therefore you have R cross R prime is 0, and you're left with R hat cross T. Okay, so this n hat to this ruled surface is just R hat cross T, R hat cross T, and if you actually look at the P we computed for the other ruled surface, for the developable surface, you'll see it's exactly R hat cross T. Okay, so there's the proof of your statement. Okay, so if we have this, what can we say? Well, the first one's easy. KUU is 0 because the SDU is 0. Okay. KUS is you dot this thing in with the SDU. So you dot R prime in with N. Okay. And KSS is simply R cross T dotted in with that guy. Okay, so let's work out the curvature for this guy. Okay, so the first step is here is C, here is my T. Okay, and what I have now is, remember, T cross N, your N hat is R cross T. Okay, so it's R cross T. So that's simply minus cos S sine of S.
Okay, but this is not necessarily normalized now, right?
This one is normalized because cos squared plus sine squared is always 1.
Yes.
Okay, so I usually compute R cross T, write it out, because often you're going to find it in different spots. But then I work out the norm as well, and I keep that. So that one is normalized. Okay, so here you have R prime. Okay, that derivative is just 0 because R is a constant. Okay, as is R double prime. Okay, so that simplifies these things tremendously, right? R prime is 0, so KUS is 0. KSS, that term there is 0 as well. Okay, so we immediately have KUU is 0 from just the fact that it's 0 over here. KUS is also 0. But we have, now this one requires T prime. And T prime, if you work it out, is simply also just N hat. Okay, and so what we have is KSS is just the normal vector N hat dotted in with T prime, and so it is 1. Okay, which is right, because this whole surface is dependent on the circle, which is a circle of radius 1. Okay, and the normal vector is simply pointing down towards the center of the circle. Okay, so that works consistently. So you can at least see in this example that this surface is curved because the curvature tensor is curved. And one of the eigendirections of this matrix actually points in the direction of curvature. And it gives you, the eigenvalue gives you what the curvature is. And that is true. So it's tremendously powerful because you can have this actively in any coordinate system. Work out the curvature, and then the eigendirections will always point, one towards the center of curvature, and the other one will actually give you the value of curvature. Okay, it's a very, very nice way. And you're going to start seeing the power of actually using these things for coordinate systems and stuff. It allows you to completely take out the dependence on coordinate systems of surfaces you're working with. Okay, so you can recognize a shape, whether it's written in a nice coordinate system or whether somebody's tried to monkey with a coordinate system and make your life difficult. You still just work out derivatives, work out the eigendirections, and there you have the curvature. Let's go back to the previous one, right? The previous one was a very strange coordinate system, okay, that didn't make sense, but it was basically describing a flat sheet of paper. Let's see if we can get that out, right? In the previous slide, the only difference was that R, I think there was a minus, anyway, R was proportional to 0, 1, 0, okay? And therefore, you had n hat, right, remember, was R cross T. So T remains this thing, okay, the curve hasn't changed, but R is now that guy, so your normal vector must lie orthogonal both to T and to R, okay, so it must point in the Z direction and it must be the unit vector, okay? If you work out the cross product, you're also going to get something, and then once you rescale it, you'll get the unit vector. Okay, T prime in this case is simply this guy again. It's no longer equals to the normal vector because that was just convenient because of the normal vector, for example, 2. But T prime written out is this thing. Okay, and therefore KUU and KUS are 0 because the second derivative of R also vanishes and the first derivative. But then this KSS, right, is then once again n dotted with T prime, but n dotted with T prime over here is 0. So there's no curvature. So you immediately see that it's flat. Okay. Right, so let me, I think I have 1 minute. So that's flat space. The definition of flat space is the eigenvalues of, in 3 dimensions, the eigenvalues of your curvature tensor, or the second fundamental form, is 0. Okay. So now you can, not a ruled surface. Suppose you have something like this, and I'm just going to give you the picture and let you stew over it until the next class. So suppose you have something, or you define a radius that's dependent on phi and theta, okay? And you say that's equals to 1 plus sine squared theta cos 4 phi over 4. And you say my surface is just going to be this R multiplied by this vector, okay? And so this vector, you'll once again realize that when I said the most general way of parameterizing that direction with unit vector, this is once again your spherical coordinates. Okay, so this just points out radially from the origin. Okay, so I have a radius that's dependent on theta and phi multiplied by this unit vector that points out. Okay, and I'm going to define that theta goes from 0 to pi over 2. So it's just the top hemisphere. Okay, and phi goes round the circle. What does the surface look like? Yeah, so if R was just 1, okay, and that's a very good guess because this is small, right? This is a quarter. So your dominant term, it's just a dome. Okay, what does this thing do?
It changes the dome.
It changes the dome. Beautiful, it changes the dome. No, that's good, that's good. What does this thing do? It gives a variation in the radius that's dependent on angle. Okay, this first term is sweet because it's always positive. The second term varies. This first term, what's it if theta is 0? 0. Okay, so there's no contribution if it's 0, right? So the top of the dome at least looks like a dome. If theta is equals to pi over 2, this thing is 1. Okay. So then if theta is pi over 2, that thing's 1, then what would this cos 4 theta do, 4 phi do? Right, remember phi goes round on the equator. Right, it can go positive in negative, and it's going to do like a wobble like this. And so, and then somebody says, I have this form for making jelly, but I want to know what the maximum and minimum curvature is of the form, because I don't want my jelly to wobble badly. Okay? So what you do is you first plot the picture. So this thing, okay, looks like that. So it's your distorted dome. Okay, and so what I will do next time is I will basically start from a parameterized surface and tell you how to go about working out, finding, even though it's, once you've got the curvature, which is just derivatives, how you work out what the maximum curvature at a point is and what the minimum curvature at the point is. Okay, and there's another nice feature that you can also, that we're also going to prove, is that at every point you can work out the direction where the maximum takes place, the direction in which the minimum takes place. They're just the eigenvectors of the curve. And those directions always happen to be at 90 degrees. Okay, so for in 2 dimensions, there's a very natural coordinate system you can put on any surface that's always orthogonal, where the one direction points in the maximum curvature direction and the other direction points in the minimum curvature direction. So if you have a malicious person that takes your ruled surface and mixes up the coordinates and gives it to you, you can go through a recipe and actually get the right coordinates that point in the minimum curvature or the straight direction and the maximum curvature direction which is curving. So you can actually get it back simply by taking derivatives, working out those matrices, then taking eigenvalues, and then that will be your new coordinates. So very nice, powerful techniques that come in. This particular friend you can actually do in a problem set, and I'll give you hints tomorrow of how to start at least. But yeah, or not tomorrow, Wednesday. Cool. Questions now? Yeah. Okay, what about this or about other things?
About the problem set.
Okay.
This content analysis, but yes.
Okay, let's go then for that. Let me just stop.